Hi, I'm Joshua Cook. I'm from the University of Texas at Austin, and today I'm going to be talking about size bounds on low-depth circuits for a promised majority. So, first, let's talk about majority. So the majority basically just counts the number of ones in the input, and if more than half of them are 1, it outputs a 1, and if less than half of them are 1, it outputs a 0. It's a component of many algorithms, and in particular, it's a component in circuit de-randomization. It's widely studied, and it's not computable by AC0 and other simple models of computation. So we can't use majority for these types of algorithms, but we can use a promise version of majority, or an approximate version of majority, or sometimes called an approximate selector, or other names. And it does basically the same thing. It's going to tell us if most of the inputs are 1s or most of the inputs are 0s. But we're only promised to output the right thing if at most an epsilon fraction of the inputs are 1, or at most an epsilon fraction of the inputs are 0. If we're somewhere in the middle, we're not guaranteed what it's going to output. Now this is often usable in place of majority. In particular, we can use it in circuit de-randomization. And it's widely studied, and this function actually is computable in AC0. So, AC0 is a class of alternating circuits. Those alternating circuits have unbounded fan-in and OR gates, and the layers alternate between being AND gates and OR gates. Then the bottom layer, in addition to x1, x2, x3, and so on, we also supply not x1, not x2, and not x3. So that way you can do negations by basically applying De Morgan's to the rest of the circuit. Then we say that the size of the circuit is the number of gates. And then AC0 is the class of alternating circuits that have a constant depth and a polynomial size. Okay, so our results focus on lower and upper bounds for the epsilon promised majority. So specifically around depth 3 circuits doing it, and we also show some upper bounds for higher depths computing promised majority. Okay, so first off, what do we have for the depth 3 upper bounds? Well, in 83, Aitai proved that there were depth 3 circuits computing epsilon promised majority. And his circuits have size slightly greater than quadratic. So it's basically n to the 2 plus this constant, where the constant is positive. But these circuits were non-uniform. And for various applications, you'd really like to have some uniform circuits so you can actually find the circuits. So in 2009, Viola found such circuits. In the special case where epsilon is equal to 1 over log n, he showed that there are n to the 4th uniform circuits computing epsilon promised majority. But if you make epsilon be a little bit bigger than that, he had to use another trick that greatly increased the polynomial, so it's much bigger than n to the 4th. We, in this paper, basically present a improvement to the 1 over log n case of Viola's circuit, and improve it to be n cubed instead of n to the 4th. Now, lower bounds are more of the emphasis of this paper. And basically, like the last slide, it showed that there are basically slightly larger than quadratic circuits. We require that you actually need slightly larger than quadratic circuits. So there's a trivial lower bound of epsilon n, and that's simply because by fixing one variable, you can eliminate one clause. And so if there were less than epsilon n clauses, you could fix the variable, the function to be 1 or 0 with fewer than epsilon n 1s or 0s, which would let you violate the promise. But Chaudhry and Radhakrishnan showed that, in fact, you require more than linear number of gates. And then Viola, in 2011, showed that if epsilon gets very close to 1/2, you start needing a very, very large polynomial number of gates in order to compute promised majority. And so our epsilon really helps out in the case where epsilon's like constantly big, but like still less than like 0.499. Okay, at higher depths, we also have some lower bounds. So first in 1990, ITI showed a uniform circuit solving epsilon promise majority, but it had bigger size, some polynomial in, and much higher depth. Chaudhry and Radhakrishnan showed that you can use that circuit in a clever recursive way in order to get very close to linear size at higher but still constant depth. But this exponent's really bad, so it takes a lot of depth in order to get close to linear, and we managed to improve how fast you can get close to linear, both in the non-uniform case and the uniform case. There are also lower bounds at higher depth. The epsilon in lower bounds still follows. And Chaudhry and Radhakrishnan also showed a nearly matching lower bound that just differs in like the order of the d. And Viola showed that if you let epsilon approach 1/2 instead of just being a constant close to 1/2, you can actually prove super polynomial lower bounds for any given depth. So since we're going to be focusing on depth 3 circuits, we're going to define some terminology specifically for them. So the first thing to notice is that the negation of a promised majority circuit is also a promised majority circuit. You can just apply De Morgan's and everything checks out. So we're going to assume that the lowest level gate is an AND gate. So then we're going to call the input bits variables. The first level gates is clauses. The second level gates is DNFs, and the last level gate is just going to be our circuit. And so our circuits is just a conjunction of DNFs. Okay. Now each one of these has a size, so the size of a clause is the number of variables in it. The size of a DNF is the number of clauses in the DNF. And the size of a circuit is the number of gates in the circuit, but we need to be a little bit more fine-grained than that. So we define bar C as the number of clauses inside of a circuit, and we have double bar C here as the number of DNFs in the circuit. This will be useful later. Okay, and finally we're going to need a couple more tools. So one is we're going to need sort of these coin distributions. So we're going to let d epsilon be the distribution that sets each bit to 1 independently with probability epsilon. So as an example, if we have d 1/3 with 3 coins, we have for each one of these outputs, we have these corresponding probabilities. And by a central limit theorem with probability almost 1/2, the epsilon will have less than an epsilon fraction of 1s. This sort of makes a connection between these coin inputs and the promised majority problem. We'll also use restrictions. So restrictions are basically strings that have 0, 1, and stars in them, and we say that the size of the restriction is the number of zeros and ones in them. So then, if we apply a restriction to a function f, basically if we see a 1 or a 0 in it, we're going to go ahead and substitute that into the input of the function. If we see a star, we're going to use the corresponding input from the function. We're just going to leave it there. Okay, so as an example, if this is our function f and we apply this restriction to it, we replace x1 and x3 with 1 and 0, and then you see that it makes this clause equal to 1 because it's the only variable into it. And since one of the clauses in this DNF is 1, it sets the DNF to 1. This clause gets set to 0 because one of the clause variables in it is set to 0. And then we can simplify the circuit by basically removing the clauses and DNFs that we fixed. And that gives us this, and this is sort of the technique that we're going to use to decrease the size of our circuit to give us our bounds. Okay. So now we're going to show the monotone depth 3 lower bounds. So we're not going to prove the exact nice bounds I gave you before. We're going to prove the simpler ones that basically just show greater than quadratic lower bounds. But you can use the same techniques that I'm going to talk here in order to show the tighter bounds if you just analyze them a little closer. So the idea is that we're going to lower bound the fan-in at each layer using some sort of deterministic restrictions, and then we're going, so iteratively we're going to build off the last one to do the bounds on the next one. So first, we're going to use a result from Viola to lower bound the clause size to log in over log of 1 over epsilon. Then we're going to lower bound the DNF size to n to the 1 plus alpha. where alpha is a constant greater than 0. And then we're going to use that to lower bound the number of clauses inside of the entire circuit to int the 2 plus alpha, where, alpha is greater than 0. Okay, so first we're going to go through what Viola proved real quick. And basically, he proved that for any constant epsilon in DNF f, if the DNF outputs 0 on d epsilon with a polynomially big probability, then for the width that we have from before, so log n over log of 1 over epsilon, there's a restriction rho restricting at most n over log n variables, such that any clause that's smaller than w will be set to 0 by the restriction, and the probability that we output 0 once we've done the restriction on d epsilon is going to at most increase from the probability that we output 0 before. So what this will do is it'll eliminate small clauses from a DNF as long as the DNF is likely to output 0 on d epsilon, with only setting a few variables without setting the DNF to 1. Okay, so the other tool that we're going to be used largely in this paper is this greedy set cover algorithm. So basically the idea is that if we have a bunch of sets, and each set has a width w, and we fix, then there's some set of t variables that we can fix that will intersect all but at most this amount that's exponentially decreasing in the width, so the minimum size of the sets, and the number of variables that we fix, divided by the total number of variables. In particular, if S is a set of clauses in a monotone DNF F, and rho is a restriction that restricts the variables to 0, then after we apply the restriction, it's going to decrease by a factor of e to the minus the width times the number of variables restricted over n. So how do you actually prove this? Well, we just start with, so let's just do a DNF here, and we'll choose the variable that's in the most clauses. So that will be in at least, the width times the number of sets divided by n. That's the average number of clauses that a variable's in. So we'll set this one to 0. That'll set all these clauses to 0, which will make our DNF smaller. So if you look here, the resulting S1, after we've done this restriction, it'll get smaller by this average factor here, which will be less than this exponential. Okay, we apply it again, and we will get rid of another one. We get rid of those, and if we apply it t times, then it'll get exponentially smaller. Yep. Okay. So now we want to show monotone DNF size lower bounds. And the idea is that if we have a DNF that's always going to output a 1 if there are only at most epsilon n zeros, but on our coin input d epsilon, it has a high probability of outputting 0, a polynomially high probability, then f has to have at least n to the 1 plus alpha clauses, where alpha is this constant that's greater than 0. So the things to notice about these two conditions is that all circuits, DNFs, in a circuit that's solving epsilon promise majority must solve this, because as soon as one of them is 0, then the entire circuit's 0, and it has to always output 1 if there are less than epsilon n zeros. And also for the DNF to really help very much in some sense, it must satisfy 2. So in particular, there has to be at least several DNFs that are satisfying the second condition. Okay, so using Viola, so now to actually do the lower bound, it's pretty simple. We use Viola's theorem to fix n over log n variables to force us to have big width. Then we use a greedy set cover algorithm to restrict these clause, so that way we have fewer variables that decrease by this factor, which simplifies to this constant that we wanted to show earlier. Then, since we've only restricted just slightly more than epsilon n over 2 variables, then there are still epsilon n over 3 more variables we could restrict to 0 before we've restricted epsilon n bits to 0. And so it has to have at least epsilon n over 3 clauses, so that way it doesn't violate condition 1. So when we put this together, this implies that the size of f has to have at least n to the 1 plus this positive constant number of clauses. Okay. Now we can apply all of this together to get our circuit size lower bounds. And so the idea is we're going to eliminate DNFs with clauses in the same way that before we were eliminating clauses with variables. And the idea that we're going to get from this is that we can eliminate too many DNFs with few clauses if there aren't enough clauses. Okay, so first, in order to do this, we're going to have to make it to where we can reasonably afford to fix a DNF clause to 1, so we need to get rid of all the big clauses. But that's easy using our greedy set cover algorithm. So we're going to focus on large clauses, those that are bigger than log of n squared. Then we're going to use a greedy cover algorithm to fix c times n over log n variables with a restriction rho, so that whenever we restrict it by that restriction, it decreases by, an exponential factor in its width times the number of variables we restrict over n, which just simplifies to being 1. And since that was a strict less than over here whenever we apply the restriction, that means that the number of clauses after our restriction are 0. So since f prime was the number of clauses that were bigger than log n squared, c must have no clauses bigger than log n squared after we apply the restriction. And we can do a very similar algorithm for a non-monotone circuit. So this isn't really a barrier. Okay, so now to prove the entire monotone circuits, the idea is to remove all the large clauses, then use the DNF lower bounds to get each clause is bigger than n to the 1 plus alpha, and then we're going to fix whole clauses to apply a set cover algorithms and argue that many clauses must be around to not eliminate all the DNFs. An issue is some of the DNFs might be small, but again, we're going to focus on the large DNFs during elimination, so some large DNF must survive if we only use few variables. So, going straight into this, so let's C be a circuit that solves epsilon promise majority. So first, apply a restriction to get rid of all the large clauses. Then we are going to only focus on C prime, which only has the DNFs that are bigger than n to the 1 plus alpha after we apply our restriction. Then we're going to use a greedy cover algorithm to select n over log n cubed clauses and set them to 1 in row 2 so that the number of DNFs after we apply the restriction decreases by a factor that's exponential in the number of clauses in a DNF times the number of clauses we fix divided by the total number of clauses. Now, since after we apply these two restrictions, we still solve an epsilon promise majority, very nearly, because we've only fixed 1 over a log n order number of variables. If we don't already have n cubed DNFs, then by a counting argument, there must be some DNF that's going to output 0 on the epsilon with polynomial probability, so it's going to have the size n to the 1 plus alpha. So C prime after we restrict by row 2 is going to be greater than 1, and then in order for this inequality to hold, we need to have C prime to be big enough to overwhelm the n to the 2 plus alpha factor on the top. So we have to have greater than quadratic number of clauses in our circuit. Okay, so in order to generalize this, we're going to use the same idea as the monotone circuit. Okay, exact same. So bound at each level, use restriction from set cover algorithm. So the clause lower bounds still work. The DNF lower bounds still work. Almost. One of the issues is that the DNF might be set to 1 earlier than we wanted to. Then we can't argue that there are restrictions left in any clauses, but we'll discuss how to fix that next. The circuit lower bounds still work. At worst, it might shrink or eliminate DNFs and clauses early, but that's not really an issue. Okay, so the idea in order to get the probabilistic restrictions is to define a sequence of restrictions, each restricting one more variable, such that each restriction in the sequence samples one variable from the epsilon. It chooses the variable so that it has a good chance of eliminating many clauses, and then we only focus on deleting clauses bigger than W. So then to use the greedy set cover algorithm to choose the variables just like in the monotone case, but now we just set them to 1 with probability epsilon instead of always setting them to 0. By turn-off bound, this will eliminate many clauses with high probability, and it will have the same probability of outputting 0 as if we sampled everything from the epsilon. Okay, now to briefly overview the upper bounds, the idea is that we're going to amplify the promise, and then iteratively reduce the size with promise majority. So we're going to use random walks on expander graphs to amplify the promise to 1 over log n over d. This only increases the size by polylogarithmic factors, which we're ignoring. Then we're going to separate the inputs into groups. We're going to run a depth 3 1 over log n promise majority circuit on each group. And then we're going to repeat d times to get this decreasing size. If we use ITIE's depth 3 circuit, then we'll get this size, and if we use our depth 3 circuit, we'll get this size. So the amplification, it's easy to do this amplification with the depth 2 circuit. The idea is just to take a majority on short walk on an expander graphs. Viola also used this idea for his depth 3 circuits, and then we're going to use short DNFs to explicitly compute the majority. And since we're only doing this on O of log n log n bits, then it's only going to have a polylogarithmic size in the DNF. And then an expander turn-off bound proves that the amplification gives us the new promise input. And the motivation, of course, is that if you set epsilon to be 1 over log n, we get much better promise majority circuits. So to demonstrate how we do the decreasing of the size, we are going to basically just put it in the groups, run a promise majority on each one of the groups, and that'll give us a new input, and then we're going to run promise majority again. The issue is that if we have a large epsilon and our delta is not too great, then we might end up getting something that's not the promise. But we can actually control that, so if epsilon is significantly smaller than the delta in the promise of the majorities, then our inputs will still satisfy a promise, and then we can do the amplification will work, and we can still output something that works. Okay, and basically, if we have a depth 3 circuit with these exact parameters, then we can get a depth k circuit with these, or depth 1 plus 2k circuit with these parameters. We combine them with our depth 2 amplification, we get our upper bounds. Okay, so the best known depth 3 uniform circuit, because we want uniform circuits, comes from Viola, and it uses some random walks on expanders to get our promise. We use a more efficient way to use those random walks to get our depth 3 circuits, and then we use those to get our small uniform upper bounds for larger depths. Okay, so there are still some open bounds. If we wanted to prove some fine-grained trade-off in depth versus size during de-randomization, particularly if quadratic de-randomization costs depth 3, we wanted to know if it does. So we did show that existing de-randomization techniques will require depth 3 to get quadratic de-randomization, but that might not be the only way to de-randomize. So we also didn't find explicit depth 4 quadratic size circuits. This seems like it would be related to some other pseudo-random objects, so it'd be interesting to study. The results aren't tight. The upper and lower bounds don't match. The best circuits, we haven't proved that they are monotone. They seem like they should be. We haven't proven that our optimal size circuits can be uniform, and our asymptotically upper bounds and lower bounds aren't exactly the same for large depth. The trivial lower bound is just n. ITIE gave this sort of curve. Chaudhary and Radhakrishnan gave this slightly better than the trivial lower bound. Viola gave this uniform upper bound, and he gave this lower bound that shows that it gets exponentially big when you get close to 1/2. We showed this nice lower bound that looks very similar to Viola for monotone circuits, and this one for non-monotone circuits. And we improved Viola's upper bounds down to cubic size. Now, it's still an open question of like where the ideal circuit comes in. It's going to be somewhere between these three, but we don't know where. Okay, and that's the talk